All right, welcome. In this briefing, we are going deep on the engineering principles and performance of combined heat and power systems. Really understanding the nuances of CHP is critical for any energy professional, so let's just get straight into the numbers. Okay, so let's dive right into the core value proposition of CHP. The contrast you see here in fuel utilization is, well, it's stark. A conventional power plant typically converts only about a third of its fuel into electricity. Think about that. The rest is just wasted as heat. But by capturing that thermal energy, a CHP system dramatically, and I mean dramatically, increases total fuel utilization to somewhere between 70 and 80%. It's a fundamental shift in efficiency. Now, just to make sure we're all on the same page, let's lock in the precise engineering definition. CHP, which you'll also hear called cogeneration, is the simultaneous production and use of useful mechanical energy, which is typically converted to electricity, and useful thermal energy. And the key is that it all comes from a single integrated system. This sequential, cascaded use of energy, that's the secret sauce right there. So this efficiency advantage is, of course, the primary engineering reason for deploying CHP. But it's actually more profound than just simple energy conservation. We're really talking about maximizing Exergy, which is all about the quality and the potential for useful work by cascading that energy through multiple useful cycles. And this right here, this number brilliantly illustrates the quantitative gain. In one specific setup, a back-pressure steam turbine CHP system, the incremental first-law efficiency of generating power is a staggering 83.3%. Now compare that to a conventional condensing station at just under 36%. By integrating the heat delivery, the effective efficiency of the power you're producing becomes absolutely immense. So, how are these systems actually put together? Let's dig into the thermodynamic foundations, because the sequence of energy conversion is what defines a system's entire configuration and ultimately its application. The most common configuration you'll see is the topping cycle. It's pretty straightforward. First, you combust fuel to generate your mechanical or electrical power. Then, the rejected heat from that prime mover, whether it's hot exhaust gas or engine coolant, is recovered for your thermal processes. So simple, right? Power first, heat second. On the flip side, you have the bottoming cycle, which you'll often hear called waste heat to power. It does exactly what it sounds like. It flips that sequence. Here, the fuel is first directed to a high-temperature industrial process, maybe a furnace or a kiln. Only then is the leftover thermal energy from that process recovered to produce power as the secondary step. So this time it's heat first, power second. Ultimately, what really defines these configurations is their energy conversion sequence and the thermodynamic cycles they're built on. This table sums it up perfectly. Topping cycles put power first. Bottoming cycles prioritize the heat. And then you have combined cycles, which are a bit different. They integrate two distinct power stages before you even get to the heat recovery. Now, that combined cycle is a really big deal, especially for large-scale plants. It's so efficient because it leverages both the Brayton cycle from a gas turbine and the Rankine cycle from a steam turbine. In a typical setup, you'll get about 70% of your power from that primary gas turbine, and the other 30% is generated by the steam turbine, which is literally running off the gas turbine's waste heat. It's incredibly clever. Okay, so moving on from the theory to the hardware. The choice of the prime mover, well, that's the heart of any CHP system design. Let's really analyze the core engineering trade-offs between the main technologies out there. This comparison really gets to the critical trade-offs. Take a look at gas turbines. They offer really high-quality heat and the lowest operations and maintenance costs, which makes them perfect for continuous industrial operations. Now, contrast that with reciprocating engines, which give you a higher electricity-to-heat ratio, better for a site that has a huge power demand. And then you have fuel cells over here, which boast the highest electrical efficiencies of the bunch. At the end of the day, system selection is always a function of matching these characteristics to an application's specific thermal and electrical needs. This characteristic of fuel cells, this is a total game changer. Because they generate electricity through an electrochemical reaction instead of combustion, they have extremely low emissions, and that makes them a critical technology, especially in places where air quality is a primary design constraint. So engineering performance is one thing, right? But it's the financial metrics that determine if a project is actually viable. A system can be technically brilliant, but it's the economic analysis that actually gets it built. Before we dive into the metrics, it's really critical to distinguish between energy and exergy. The first law of thermodynamics tells us energy is conserved, fine, but Exergy focuses on energy quality. It's the maximum useful work you can possibly extract. The real strength of CHP isn't just in conserving energy, it's in minimizing the destruction of Exergy, which means you're maximizing the work potential of every bit of fuel. Any rigorous engineering evaluation is going to rely on these 4 KPIs. The heat-to-power ratio is fundamental. It's how you match the system to a facility's specific load profile. Once it's installed, the capacity factor tells you how well you're actually using that asset. And from an efficiency standpoint, the heat rate gives you a direct, inverse measure of how effectively the system is converting fuel to electricity. Together, these 4 really paint the complete performance picture. Now, when it's time to evaluate the investment, it is vital to move beyond the simple payback period. I know it's easy to calculate, but it's a very blunt instrument. A life cycle costing approach is far, far superior because it accounts for the time value of money. And this is crucial given that energy costs can represent 70 to 90% of the total cost over a project's lifetime. And the source material gives us some really clear economic thresholds. To get an attractive payback period, say 3 years or less, under continuous operation, a project typically needs 2 things: displaced electricity costs of at least 10 cents per kilowatt hour and natural gas costs below $6 per MMBTU. Those are the numbers that really make the project pencil out. Of course, this economic viability doesn't exist in a vacuum. It's heavily influenced by the regulatory context. Back in the early 1900s, CHP was dominant. But by 1974, it had fallen to just 5%, mostly due to the rise of big centralized utilities. The real game changer was the 1978 PURPA legislation. That law mandated that utilities had to buy power from cogenerators, and it basically catalyzed the entire modern resurgence of CHP. And looking forward, federal goals are signaling a continued major push for expansion. The Department of Energy has stated a goal for CHP to make up 20% of the nation's entire generation capacity by 2030. A policy driver like that points towards a very robust future for CHP in the national energy portfolio. So all of this leaves us with a critical strategic question. Given CHP's unparalleled efficiency but its reliance on fuel, what is its ultimate role in a decarbonizing grid? Is it a transitional technology, a bridge that maximizes efficiency on our way to a zero-carbon future? Or, with things like renewable fuels and hydrogen on the horizon, can it become a destination technology in a true net-zero energy system? That right there is the core question facing the entire industry today.